The next talk of today is going to be by Kathleen Larson. Kathleen recently completed her PhD in biomedical engineering at the Medical Image Computing Lab at Vanderbilt University. Her dissertation focused upon developing techniques for improved surface-based cortical thickness measurement to better quantify gray matter atrophy and the natural history of Huntington's disease. She is now a postdoctoral research fellow at the Martinos Center, where she continues to research longitudinal surface-based analyses. Outside of the lab, Katie partakes in a plethora of hobbies, including distance running, rock climbing, baking, and knitting. Katie, over to you.
Hi, can everyone hear me okay?
Yes.
Okay, cool. Gosh, it's been a long time since let me share my, great. Can everyone see my presentation?
Yes.
Okay, cool. Yeah, please interrupt me if comes any streaming problems here. But yes, thank you for inviting me to give this talk and for that introduction. The title of my presentation is Research-Based Synthetic Atrophy for Accuracy Validation of Longitudinal Cortical Thickness Measurement. So the work that I am going to present it was the first project of my dissertation research and kind of laid the foundation for everything that I eventually did throughout my PhD. So, like you said, the main focus of my dissertation was on gray matter and gray matter thickness. So usually it's going to be between like 2 and 5 millimeters in different regions of the brain, but it changes within age and pathology. And so I was specifically interested in how that cortical thickness is changing throughout Huntington's disease progression. So measuring which parts of the brain are changing at which time. Huntington's disease, as a little background, is a neurodegenerative disorder that's primarily associated with motor deficits. And those motor disorders are mainly linked to subcortical atrophy, but it's also associated with cognitive and behavioral symptoms that are linked to gray matter atrophy. Unfortunately, these changes aren't well quantified in the way that the subcortical atrophy is. So the overall hypothesis of my dissertation was that creating an improved method to quantify these gray matter changes would lead to a better understanding of Huntington's disease progression. So I was mostly interested in measuring gray matter thickness then. And there's a couple different ways that we can do that in a 3D MRI. Firstly is volumetrically. So that is where we compute the thickness directly within the image space, like you see in this example below. And then there are surface-based methods, which are computed by measuring the distance between gray matter and white matter surface reconstructions. This is what FreeSurfer is probably most famous for, creating these cortical reconstructions and measuring the thickness between them. There are some pros and cons in each. So volumetric methods are generally considered to be more computationally efficient, but surface-based methods are considered to be more robust against things such as image noise or topological defects. So the focus of my dissertation was developing a new surface-based method for cortical thickness measurement. However, anytime you create a new method, that requires validation. Reproducibility is something that's really easy to measure because if you have a test-retest data set, like this example, you have images of the same subject on the same day. And ideally, there should be no brain changes between these two images. So if you apply your thickness measurement pipeline to both of these images, any change that you detect is going to be the reproducibility error of your pipeline. Accuracy, however, is much harder to assess, and that is primarily due to the lack of good ground truth data. Sometimes people have used histology to look at the accuracy of their thickness measurement. So how close is my algorithm getting to the thickness that we've measured using histology? But there's a lot of issues with this, such as tissue fixation can cause deformation in tissue, and also histology is a two-dimensional modality, whereas cortical thickness is an inherently 3D metric. Sometimes people have compared their results that they get to those of previous methods, but you can't really use results from a previous method to say that, okay, my results match this method. There's no way that you can then go and say that my algorithm is more accurate than that method. So people have turned to something called synthetic atrophy. So creating synthetic changes in image data to create a ground truth data set with known changes in thickness. And this has been primarily achieved using both traditional and deep learning methods in a volumetric context, but not in a surface-based context. So my goal and the idea of the research that I'm going to present is creating a ground truth data set with synthetic atrophy that is specifically designed for surface-based methods rather than volumetric. At a glance, my synthetic atrophy method has 3 main steps. So firstly, you induce localized synthetic gray matter atrophy in a brain MRI. And then you take the deformation that you used to induce the atrophy and you apply it directly to cortical reconstructions from the original image data. And then once you have a surface for the original time point and the atrophied time point, you can measure the induced change between those 2 surfaces. And that induced change is going to be your ground truth change in cortical thickness. To do the synthetic atrophy induction, the way that we started that is first generating a cortical parcellation from a T1 weighted image and selecting a ROI. I am using the Desiccan-Killian atlas produced by FreeSurfer, and I've selected the superior temporal gyrus to show you as an example, but you can do this with any cortical parcellation that you want. With this ROI, you erode a binary mask to create an atrophied version of that ROI. So you can erode this iteration pipeline as many times as you want to induce however much atrophy you want. Because each time that you do this, it is a series of binary mathematical image operations to basically slough off one outer layer of the voxel. And I actually did this in a super resolution space. So I increased the resolution of these ROIs by 400%. And so I was basically trying to induce subvoxel amounts of atrophy between each iteration. With the deformed and original ROIs, you can register the original to the ROI or to the atrophied to kind of push that gray matter boundary inward to yield a deformation field. Finally, I masked this deformation field so that only the area inside of the gray matter and the surrounding CSF was going to be affected. I didn't want the deformation to affect the white matter or any of the surrounding gray matter, only the ROI in question and the surrounding CSF. With this transformation, we can then apply it to the original image data if you want. So I'm going to focus in on the superior temporal gyrus, and I'm going to go back and forth between the atrophied and the original time point. And you can see that, yes, we are deforming the gray matter inwards, and it looks like we're not affecting the surrounding tissue that much. So that's good. But I want to be looking at surface-based data and not image-based data. So we're going to take that we're going to take the original image and then we're going to generate surface reconstructions from the original time point. I have the ROI that I want to deform in pink and everything else is going to be in green or yellow. Then with the deformation, I can apply that directly to that cortical surface to create a surface reconstruction for the atrophied time point. And then with these 2 sets of surfaces, I'm going to measure the true induced change between these surfaces. The way that I've quantified the true ground truth change is through something called the mean surface displacement difference, the MSDD. And what that is going to be is the mean closest distance between the original and atrophied surfaces. So for the gray matter, we have at each vertex, we measure the distance from the original surface to the atrophied surface, and then the atrophied to the original, and we take the mean of that. And then we do the same thing in the white matter. And we notice that in this PowerPoint example, the white matter is a lot closer to between the original and the atrophied than in the gray matter, because ideally the white matter surface should not be moving at all. And then the true change is going to be the displacement experienced by the gray matter minus the displacement experienced by the white matter. And something really critical about this is that notice that at no point in quantifying ground truth change in cortical thickness did I actually calculate cortical thickness. This is really important because that means that my method of defining ground truth change is not going to be biased towards any one thickness calculation method. When I went to validate my method, I had 2 questions that I was answering. Firstly, I wanted to know how localized is the atrophy to the target ROI? Is the deformation only constrained to the ROI that I was looking at, or is it bleeding out into the surrounding regions? Secondly, I was interested in how much atrophy can I actually induce? to study this, I looked at the NITRC Kirby test retest dataset. That was the reproducibility dataset that I mentioned earlier. And I basically just needed a data set of healthy controls. So I took one image from each of those, one of the test retest images from each subject. And first, I looked at how localized the atrophy was to the target ROI. So I measured the MSDD in 3 different labels. I have the bulk of the brain is green. And then I have inside of the ROI in question is in pink. And then I have the surrounding vertices are in yellow. And I wanted this to be its own ROI so that I could see how much the deformation is affecting these voxels. Because if I only did inside and outside the ROI, any changes here would be averaged out to 0 because of how many other vertices are outside of the ROI. So to look at this, I varied the number of erosion iterations from 1 to 12. Each iteration is inducing about 0.5 millimeter of atrophy, which should theoretically erode the entire cortex. But due to the regularization parameters of a deformation field, it won't actually remove the entire gray matter cortex because the image transformation doesn't allow that part to collapse fully. So what we see with increasing iterations is in the green region, we see that there is virtually no change no matter how much atrophy we're inducing because the atrophy is not affecting those vertices. In the pink region, we see that we have a linear change in induced thickness up until we get to a certain point, and that's going to be the maximum amount of atrophy that we can induce within that region. And then in yellow, we see that we're getting a very slight increase in thickness change, but nothing significant. So that means that the ROI or the atrophy is in fact being localized to the target ROI and not affecting the other regions significantly. Next, I wanted to see how much atrophy can we actually induce within those images. Recall that on this slide, we saw that it was approaching some asymptote, and this asymptote was not equal to the original thickness in the region. So I wanted to look at the maximum MSDD in each of these cortical regions. And I looked at the amount that we can induce with each of these regions, but I'm only going to show you the maximum and not like the intermediate values. So what we see here is we see that we can induce up to 0.25 millimeters of atrophy within these regions. And what I found was that the amount of atrophy that we can induce corresponds to the original thickness of the region. And that makes a lot of sense. So in the thicker regions, such as the temporal lobe and the frontal lobes, we see that we can induce more atrophy. And vice versa, we see that in the thinner regions, like the post-central gyrus and occipital lobes, we cannot induce as much atrophy, which makes a lot of sense. And this added up to about 40 to 70% of the atrophy. And the exact amount is kind of based on a lot of different properties like curvature of the regions, et cetera. But we didn't explore that too much in the publication for this. So if you wanted to go and apply this to a new thickness method, such as what I did for my dissertation, what you would do is you would run the synthetic atrophy pipeline to generate your ground truth data. And what you want are those sets of cortical surfaces with known change in thickness within a set of cortical ROIs. You would then measure the thickness with your new method in the original and the atrophied surfaces. And any error in accuracy is just going to be the difference between cortical thickness that you measure and the MSDD, that ground truth thickness change. So now that I had this for cortical thickness, I then went to go apply this to cortical segmentation accuracy, because that was also something that I was looking at a little bit during my graduate school work. So one way to look at cortical segmentation accuracy is comparing your surface placement to manually placed fiducial landmarks. This is an example of what these landmarks would look like in a T1 weighted image. So we have a set of landmarks denoting the gray matter white matter boundary, and then a set denoting the gray matter CSF boundary. And when you want to measure your segmentation accuracy, you can perform cortical segmentation of this image and then measure the distance between your surface and those landmarks. And then that distance is going to be your accuracy error. Unfortunately, only cross-sectional data exists for this. So there was no way to apply these methods for longitudinal cortical segmentation because there was no longitudinal data set like this. So I used my synthetic atrophy pipeline and I applied the atrophy-inducing deformation to both the image data and the landmarks. And so what this did is it created a longitudinal data set with cortical landmarks for each time point. And moreover, these cortical landmarks have exact correspondence between each time point. So I don't know if you can see my mouse, but the top landmark for the gray matter out here corresponds to the top landmark for the gray matter on the atrophy. And then you can perform longitudinal cortical segmentation and surface reconstruction for both time points. And again, your accuracy is going to be the signed or unsigned distance from those landmarks. So in this case, the sign of the distance is basically going to correspond to, are you overestimating or are you underestimating surface placement? Now, while you're looking at this data, you might think, your atrophied time point does look worse than your original. And I did notice that while I was doing my research. And so I was worried about that. So I was wondering, is the atrophy in pipeline creating artifacts that are negatively affecting the segmentation? Or is it just that segmentation is harder to do in unhealthy data than in healthy data? So to look at this, I applied my method, the synthetic atrophy method, to this entire data set with fiducial landmarks. It's called the validation data for cortical reconstruction algorithms from Johns Hopkins, and it has 10 subjects total. 5 of them are healthy controls, and 5 of them are MS subjects. Each subject is associated with a T1 weighted image and with 7 sets of these cortical landmarks for each surface and hemisphere. They're in all 7 different regions of the brain all over. And because there's 7 sets, 2 surfaces, 2 hemispheres, each set has 30 landmarks. And then there were 2 landmark placers or raters. This yields about 1,600 landmarks per subject. So that's a lot of data. To process this data, I applied the assay pipeline to the image and landmark data. And then I performed free surfer cortical segmentations for both image time points. Once I had these surfaces, I performed statistical analyses on the unsigned and signed segmentation errors for this. And what I was interested in looking at is the original healthy control data, the synthetic healthy control data. So that is the synthetic atrophy pipeline applied to the healthy control data, and then the original MS data. And what I wanted to see is, does the synthetic atrophy data have a worse segmentation error than the original MS data? So we're basically looking at synthetic atrophy versus naturally occurring atrophy. I also wanted to look at cross-sectional segmentation versus longitudinal segmentation results, because my theory was that if the longitudinal results were a lot worse than the cross-sectional results, perhaps there's some issue with my pipeline that is inducing artifacts that is messing up the way that FreeSurfer does its longitudinal segmentation. And then I also wanted to look at inter-rater variability just as another metric to see if I should be combining these results or keeping the raters separate. And so this is an example of what I did for each set of landmarks. I have a set of signed errors in this case for the 3D and 4D and both different raters in the original HC, synthetic HC, original MS, and synthetic MS data. The main takeaways from the statistical analysis were firstly that the healthy data yields the best performance. That's obvious. We expected that. And then we also found that there were no significant differences in error except for one region, one like set of landmarks between the synthetic or the naturally occurring atrophy. So I took this to mean that my algorithm was not inducing error that would affect the cortical segmentation results more so than naturally occurring atrophy would. And then I also found that there were no significant differences between the 3D and 4D segmentation protocol results or between raters. So with the 3D and 4D results, that is a good thing. That meant that my the atrophy data that I created wasn't interfering with any of the initialization processes for longitudinal segmentation. So there are a couple limitations to my method, and they're mainly caused by the issues with registration-based methods. So firstly, there's an issue where registration-based methods that use deformation apply, or like they rely on interpolation to create the new image. And that interpolation is going to create a blurry boundary. You can see the CSF gray matter boundary in this region at the top of this gyrus here is sharper in the original image than it is in the atrophied image. And also, it's really difficult to resolve CSF within these deep sulci. And what I mean by that is, in the original image here in the middle, you see that we know that these are two separate gyri, so there should be CSF existing within here. But because of partial volume effects, you can't really see it very well. And so when I go to induce atrophy in that region, it's trying to push the gray matter inwards. Well, what that means is that it's trying to expand CSF in this region, but because there's no CSF, it's really just expanding the gray matter on the opposite sulcus or opposite sulcus. And that's a problem when I what I should be seeing here is CSF and not gray matter. So I worked on a project with a colleague from my grad school lab where we used inpainting to synthetically create CSF in those regions. For those of you who are unfamiliar with this, inpainting is an image processing tool that basically replaces patches or voxels with an image within an image. And the most common example of this is removal of brain tumors or MS lesions from an MRI and replacing those areas with healthy tissue. There are a lot of both traditional and deep learning methods to do this, but the deep learning methods are primarily related to 2D and 2.5D CNNs. So what we did, or what my colleague and I did, was create a CSF inpainting technique that uses a self-supervised 3D GAN. And the goal of this was to improve the gray matter CSF boundary resolution. So the way that we would use this is to apply the synthetic atrophy pipeline to get those deformed images. And then that would also yield the ground truth change encoded in the transformation. But then you could apply this inpainting tool afterwards to kind of clean up the image and improve boundary resolution. That was the main idea of this. I'm not going to get super into the technical aspects of the network because that was my colleague did most of the network training, and then I would take his network and use it, and I did all of the validation on the atrophied surface data. But I do want to highlight the technical contributions from this work that it was presented at Middle this past summer. So firstly, it was the first use of inpainting for this kind of CSF-based application. Secondly, the model that we generated is capable of doing multi-label inpainting, and it's not restricted to only CSF-based inpainting. And this is because the network was trained on multi-label tissue maps and not just CSF tissue maps, even though the downstream task was limited to CSF. Finally, we combined several different 2D methods and extended them to 3D for the first time. So these methods include a self-supervised dropout training framework, and the idea was to increase sample size during our training. We used an edge map of the input T1 image, and the idea for that is that these have been shown to improve the inpainting of fine details in the resulting synthetic data. And lastly, we also incorporated 3D sinusoidal positional encoding. And what this does is I like to think of it as it kind of helps like the big picture versus fine detail in painting through improving the spatially inducted bias in multi-scale image data. So like I said, I'm going to mainly focus on the way that we validated this. So what I did was I induced synthetic atrophy in 7 different cortical regions, and I wanted to capture a wide range of regions. So those that both are surrounded or have a very clear CSF borders on the outside of the T1 image, like on this side, and those that were surrounded primarily by gray matter, like in this hemisphere. And what we were looking at for our validation metrics were both the resulting image quality, so qualitatively, how do the images look, and then also quantitative data, including L1 loss, PSNR, and the structural similarity index metric. And in addition to the image quality, we also looked at the accuracy of the measured thickness changes in the synthetic image data. And what we did was we compared our methods to a baseline where there was no inpainting involved. We looked at 2D and 2.5D CNNs, and then we also looked at 2D and 2.5D large mask inpainting called LEMMA, and that was the current state of the art at the time of publication. And I want to note that notice that the reference for this is only attached to the 2D, and that's because my colleague actually developed a 2.5D extension himself and only used because that was not published at the time, but he wanted to have a 2.5D comparison for the LAMA in addition to the CNN for completion. So to look at the qualitative image data, what we have here is an example of the gyrus that we were looking at. So this is the T1 weighted image with synthetic atrophy induced, and beside it is where the CSF data is in there. The 2D CNN and 2.5D CNN in painting both resulted in pretty sharp boundaries here. So we see that like it's pretty unrealistic how different the CSF tissue is between the gray matter. So that didn't really work very well. And it's even more pronounced in the 2.5D. And then in the lemma, it looks a little bit better, but especially for the 2.5D, it looks pretty good, but we still see that high resolution or the sharpness there. And then in the 3D CNN, and this is our main contribution, it's the image quality itself doesn't look that good in this region. But we don't see that sharpness of boundary. So we were kind of playing with like, how sharp do we want these boundaries to be versus how dark do we want the CNN to be? We found that of all of the images here, the 2.5D lemma had the lowest L1 loss, but the 3D CNN data had the highest PSNR and the highest SSIM. So our main takeaway that these two both yielded the best results. And that's why we used both of those to look at the accuracy of synthetic image data for cortical thickness measurement. To look at this, we performed longitudinal cortical segmentation in 3 different iterations. So the first was, but all of them used the original image as the first time point. So that has no atrophy in it. And then the second time point for longitudinal segmentation, we used the 3D CNN image or the 2.5D lemma or the no inpainting images. So we have 3 different sets of cortical surfaces that we're going to measure thickness in. And we measured the thickness change between those time points to the ground truth change in each of those 7 atrophied regions. And what we found was that the 3D CNN did in fact outperform lemma in this downstream task here. So in all of these regions, we see the 3D CNN is in pink, lemma in yellow, and no inpainting in green. And so, yeah, we found that the free surfer did perform better than the inpainted data, than the no inpainted data, primarily in regions surrounded by other gray matter areas. But it performed worse in regions like the precentral cortex here and kind of in the superior temporal gyrus in regions that had well-defined CSF. So basically what we found from this was inpainting CSF in regions that already had good CSF didn't really make much of a difference. But inpainting CSF in regions that were surrounded by gray matter, so those regions where CSF didn't exist already, did vastly improve the thickness measurements that we got. So in conclusion, the work that I presented here was a ground truth validation framework for longitudinal surface-based cortical thickness measurement. And the key aspect of this was that it focused on change in thickness rather than the raw thickness at each time point, and was notably unbiased to any existing thickness method. Then I showed how I extended this method not only for the accuracy validation of thickness measurement, but for longitudinal cortical segmentation. And finally, I showed how we applied a novel 3D GAN network to improve the image quality via inpainting, particularly in regions surrounded by gray matter where CSF was not originally present. And also, if you are interested in learning more about this, all of the code for these methods is on our lab GitHub. We were really big into open source data and providing all of our resources to be publicly available. So if you're interested, I encourage you to reach out to me and I can direct you to our GitHub. And I'd like to acknowledge my funding I had in grad school and my grad school lab, particularly Ipek Oz, my wonderful thesis advisor, and Jia Cheng Wang, the colleague who was working with me on the inpainting. And I also want to give a shout out to my new lab, the Laboratory for Computational Neuroimaging, my co-advisors, Bruce Fischel and Doug Grieve, and Sean, who is my informal mentor right now and also invited me to give this talk. So thank you. And I will open the floor up to any questions if you have them.
Online?
We'll start with a question by Hassan.
Oh, okay. Yes, I see that. Okay, so yeah, a question from chat, I'll read out loud. The synthetic atrophy that was applied seems to be homogeneous, constant erosion, and not varying spatially. And the question asker is asking, is that a clinical observation? So does atrophy generally occur that uniformly in a clinical setting and not just in the synthetic data? And does this have an impact on the tool for validation? So no, it does. Like atrophy does not occur this uniformly in real data the way that it does here. And you could basically replicate naturally occurring gray matter atrophy better with smaller ROIs and kind of varying the amount of atrophy that you're inducing within those regions. So in one region, maybe doing 2 iterations, and another doing 1, another doing 4. But then the second part of the question was, would that have an impact on the capacity tool for the validation? And my answer to that is, I don't think so. The only way that it would is if you had vastly different, I don't think that the amount of atrophy induced varies enough between regions such that it would significantly impact your validation. It would only be if you had such severe atrophy in one region and not in a neighboring one that the surface placement wasn't able to be accurate, I think. But yeah, thank you.
From the audience.
Thank you very much. That was a really cool talk. You presented the validation basically, like really neatly comparing it to a case where you had been able to generate your synthetic atrophy and compare it to actual atrophy. What I'm curious about is have you done or have you looked at the comparison of your synthetic generation with the addition of inpainting CSF to the accuracies that you see on real data where you have got actual atrophy as well?
No, I did not look at so yeah, I didn't do that. That's because those were parts of 2 totally separate projects. So we didn't end up having room to include that stuff in the middle submission was limited to 8 pages. So there was just simply no room for that. But that would be really interesting to look at how the inpainting affects the quality of the images compared to naturally occurring atrophy. But yeah, we did not.
We have no more questions. Next speaker.
Yeah, thank you so much for listening again. I'm gonna unshare my screen now.